So today we're going to finish up with the quantum key distribution, and then let's see if we can start a little bit on the entanglement, another very important subject in quantum computing and quantum information. And then so today we're actually going to first start to finish up here, and then on the COOTAC section, okay, I will show you guys the latest examples for the quantum key distribution systems that just came out this few years. Okay, so last time, just a little bit of rewind. Last time that we learned quantum key distribution. Okay, the first thing is that it's distributing a key. Okay, instead of sending information from A to B or B to A. Right, so the key can be co-generated as long as A and B has the same information, has the same bit. Right, it's a key. It doesn't matter what the key is. And the quantum key distribution is supposed to be theoretically 100% safe. And then the protocol, okay, we explained here is that we use photon polarization, okay, as the information carrier, and you can choose horizontal vertical basis, or you can choose 45-degree basis. So Alice, okay, generate random binary numbers, for example 0, 1, 0, 1, and then also she randomly choose the basis for each of this number, right? And then you prepare the photon, okay, for each numbers. For example, horizontal is 0, vertical is 1, 45-degree down is 1, 45-degree up is 0. Right, so prepare all these photons and then you send it to Bob, and Bob randomly, when Bob received these photons, he doesn't know what basis Alice used. Right, so what Bob does is that he also randomly chooses a basis, okay, one of these two bases, and then he did the measurement, right, and then the final step is that Alice and Bob publicly announce their basis, and then they use, and they know that if they use the same basis, then they will have the same number, right? And then they use those numbers as a key. And at the end of Tuesday, okay, we start a little bit of discussion of whether this whether this schematic, okay, this protocol is completely safe. And then here we can go in a little bit of details, okay, try to further justify that. Okay. And we can ask a few hypothetical questions to see, okay, if this type of attack will work on this quantum key distribution. The first one, we kind of say that already, okay, last time, is that if Eva has full control of the key distribution line, right, and then he can have the photon from Alice, okay, measure and then send it to Bob, can Alice extract the key? And then at the time we say that, okay, the answer is no, right, because Eva doesn't know what basis Alice used, right, so at maximum he has 50% chance of using the same basis as Alice, right? So he only gets 50% of the information, which is, for binary, it's like random, right? If you just generate two random numbers, 50% of them would be the same. And the second question, okay, is a little bit, I don't know if any one of you, actually think about this, is that can Eva do measurement not on this basis? Right, not on one of these bases. Can she do the measurement on this basis? Can she do measurement on this basis? Like one is horizontal, the other is 45-degree up. What do you guys think? So in linear algebra, we learned that, okay, you can use, for example, for two-dimensional space, you can pick two vectors, right? As long as they're not the same, right? They're not parallel, they're not pointing towards the same direction. You can use two vectors to express all the vectors in the two-dimensional space, right? A linear combination can do that. So it looks like fine, right? It's like, okay, we have two bases now, okay? They're not orthogonal, but then they are actually complete, right? You can use them to express anything. So if you think about this a little bit deeper, there are two things that actually doesn't work here, okay? The first one is that is the postulate in quantum mechanics, right? When you do a measurement of a physics attribute, and then what you can get in your measurement is the operator belonging to that, well, the operator of that physics attribute, and then its eigenstate and eigenvalue. Okay, and then if you go in there, you can actually prove that, right? We actually prove it, right? The eigenvalues or eigenstates are actually all orthogonal to each other, right? So they're naturally orthogonal to each other. And so if you define this in your postulate in quantum mechanics, so in a way that, okay, you already prevent, okay, people doing measurement with non-orthogonal bases. Now, there's a second reason, okay, more intuitive reason, is that why these spaces wouldn't work in quantum mechanics, right? If you think about this, is that, okay, now if my photon is in this state, right, horizontal state. Now the interesting thing is that if you use this basis for measurement, not only can you measure horizontal, but then this state also have 50% chance of becoming, 45-degree up, right? Because this one can be dissolved like 45-degree up, 45-degree down, right? So even if you measure one of the eigenstate, right? If you choose this basis, even if you measure your basis, you're not getting a definite answer. Right, you're getting, okay, sometimes you can get horizontal, sometimes you get 45-degree up. So your entire measurement become really random, right? Even if you choose the state, okay, even if you measure the state, which is your basis, you still get a probability result, which just cannot be used for this quantum key distribution. Okay, does that make sense? Okay, and then the next thing is a little bit more realistic now. Is that how about I measure the photon twice? Okay, and then for one time I measure it at horizontal vertical basis, the other time at 45-degree basis. Okay, and the thought is that if you only have one photon, that wouldn't work, right? Because as long as you measure it, if you're using the wrong basis, that would change the state of the photon, right? So that wouldn't work. But if you have two photons, or in general multiple photons, so for example, if the Alice did a really bad job, she's not sending single photon here, but each information, okay, she has a cluster of photon, right, to represent one information. Then this looks like a lot like classical information now. So what you can do is something called a split attack, right? After you receive the photon, if receive this photon, a lot of them, she can simply use a beam splitter to split some of the photon here and some of the photon there, right? And then Eva, she can do is say, okay, she can measure this one on horizontal vertical basis, and then she can measure the other one on 45-degree basis, right? And then the only thing that it's hard to know is that well, actually, then she actually can have the full information that Alice sent out, right? If she has enough photon. Let me explain how it works, okay? The first part is that she did this measurement on both bases, right? So what she can do is that she can wait for Alice to publicly announce the basis selection, and then he only picked the result that he used the same basis as Alice, right? So she actually has full information of what Alice sent out. But then here's another thing is that, but Alice and Bob, right, if they are using the same basis, they're supposed to measure the same result. So for Eva, okay, after you do this measurement, you need to send something to Bob, right? If Bob doesn't receive any photon, he would know that there's someone eavesdropping, right? So here, okay, the realistic attack would be if Alice does a really bad job, she sent multiple photons, and then Eva is able to measure multiple photons, okay, like keep doing the split. Okay, for each photon, she all do this horizontal vertical basis, and then for these photons, she do the 45-degree basis. And then the important information here is to know Eva needs to figure out what basis Alice used before she announced it, right? So that she can duplicate that information and send it to Bob, right? So what you will see here is that, okay, if Alice uses horizontal vertical basis, then when Eva is doing this measurement, then all these photons should be the same result, right? If the photon is prepared in a horizontal way, right? So you should get 4 zeros here, right? This is your measurement result. And now for the horizontal photon, and then if you measure it on 45 degree, okay, then you will get random number, right? And then for all of them to be 0, okay, each one of them 0 is 0.5. If it's random number, right, 50% of it being 0, and you need 4 of them to be 0, then you need 0.5 to the 4th, right? So you I think you end up with 16th. I think this is roughly 5%. Okay, so you can see that Eva, okay, if there's 8 photon coming in, Eva will have 95% confident on this photon, okay, what basis Alice is using. Okay, and then that's actually, if you think about it, okay, that's a lot of confidence, but actually no, if you send out enough number of information, and then 95% quickly accumulated, and then Alice and Bob, okay, can actually figure out if their original original agreement is like 98%, and they reduce to 95%, then they can still tell, okay, there's someone eavesdropping. So that you can see here, the key is that, okay, if you reduce the number of photons to a reasonably low level, that even Eva, okay, is able to do measurement on both bases. But then as long as she doesn't have enough photon to figure out, okay, which basis Alice is using, then she cannot duplicate that photon and send it to Bob. So Bob has a chance to discover, okay, someone is eavesdropping. Okay, and this is called, I think it's called split photon attack or split attack. And then it's kind of interesting, and right now I think for all commercial system it has been resolved. There's other ways to get over this, not using single photon. Okay, and then the third question, okay, I think we discussed last time, is whether Eva is safe, right? And then we can go a little bit in detail here. 1 second. Let me check the recorder. Okay. The question here is, what is the chances for Alice and Bob to discover, okay, there's someone eavesdropping, and we can see this as let's say this, okay, if Alice send out photon that's 45 degrees up, right, and then there are two possibilities, okay, 50% of the chance Eva would use the same basis as Alice, okay, 45-degree basis, and nothing will happen. 50% of the time, Eva is safe. But then it doesn't mean that the 50% of the time, but then the actual probability is a little bit higher than that. Okay, let me try to explain this to you guys. Okay, so if Eva, so if this is 45-degree basis, that's safe, okay? But then there's another 50% chance that Eva is measuring in horizontal and vertical basis, okay? Horizontal and vertical basis. So what will happen is that if you measure in these bases, then okay, you only have 50% chance of getting the correct result. Okay, only 50% chance getting the correct result. And your photon after this measurement will become either horizontal up or vertical. Okay, after the measurement, you'll get this, and then each one of them is 50%. Let's see how we define this. This is 0 or 1. Okay, this is 0. Okay, and then after this measurement, right, this photon passed to Bob. Okay, now Bob received this photon, and the only chance where Bob and Alice can discover Eva, or even would bother to check the result, is when Bob and Eva is using the same basis, right? Because those are the times where people where they expect, right, to see the same result, right? So Bob, if they're checking the result, then Bob must be using, the same basis as Alice, right? And then no matter which photon arrive here, Bob would actually receive a random number, right? Because it's measuring on different bases. So Bob will have 50% chance measuring 0, and then 50% chance measuring 1, right? So if you look at the overall probability, okay, when Alice sent out 0 on the 45-degree basis, and Bob, okay, also using 45-degree basis to measure it, and then Eva, okay, unfortunately used the wrong basis, okay, and the net result would be, okay, 50% of the time, Bob just do this, Eva just do the measurement on random basis, and then 50% of the time she would use 45-degree basis, which is fine, right? In this case, Alice, Bob, and Eva will have the same result. Alice and Bob wouldn't be able to discover Eva. So 50% chance safe, plus, okay, another 50% chance where Eva used the wrong basis, okay, but then in those 50% chance, okay, the Bob will receive a random number, right? So Bob still have another 50% chance, 50% times 50% chance of measuring 0. Right? So the overall probability for Bob if Alice send out 0 on 45-degree basis, and then Eva, okay, do random basis measurement. So overall, there are 75% chances for Bob to receive 0, right? 75% chance for Bob to receive 0. So what that means is that this set a requirement for the I would say for the stability or for the system confidence, right? So when Alice send out certain information, you'd better have more than 75% chance, okay, of maintaining that information when Bob receiving it, okay, even if there's no one eavesdropping, right? Think about it. If your system, okay, have noise and then Bob originally, even there's no one eavesdropping, the Alice and Bob measuring the same number, okay, if that probability is lower than 75%, then you will never know, okay, you will never know whether Eva is there, okay, to eavesdropping, because even if Eva there, she only reduced the chances of them measuring the same result to 75%, okay. So there's actually a very serious requirement on the system requirement to make this quantum key distribution completely safe. Okay. Any questions here? And the next question, okay, is that is the system completely safe? And then we kind of already answered that. And then the real reason that this is entirely safe based on two facts. One is that there's no quantum cloning. There's no quantum cloning, so that when Eva receives one photon, okay, she cannot duplicate it and then measure it on both bases. She simply cannot do that. Okay, and the second reason that really protect this system is actually based on the quantum measurement. Is that whenever you measure something, okay, you get a result, the state collapses into that eigenstate corresponding to your measurement result. So your measurement will change your state, and these two in combine, okay, provide the safety, okay, to the quantum key distribution. Now, the next question, some of you might wonder, is that why Alice and Bob can share the key, but not with Eva? Okay, someone would say, okay, Eva is just doing exactly the same thing as Bob, right? Because Eva, okay, also measures the photon randomly, okay, using random basis, and then Bob is also doing that. But why the information is shared between Alice and Bob, but not with Eva? Okay, and and the question, well, the answer to this is that you have to kind of imagine where the information is generated. Okay, if you think it in a way that Alice is sending out the key and then Bob receive it, then it's likely to cause a misunderstanding, because you might think, okay, Alice sent out something, and then now instead of Bob receiving it, Eva is receiving it. So that why cannot Eva have the same copy as Bob, right? So the truth here is that the quantum key distribution, the key, okay, is not sent from Alice to Bob. The key is generated at the moment that Bob does the measurement, right? The choice, okay, the basis choice made by Bob decide whether that piece of information is useful or not, right? If he decided to use a basis which is the same as Alice, then that will stay as a key, okay? If Bob used a different basis than Alice, okay, for this photon, then that information will be discarded, right? Because you're not getting the same result. So the information, okay, now you probably get a better understanding, is that what Eva doing here is actually useless, because when Eva tries to eavesdropping before the photon arrive at Bob, the key hasn't been generated. Okay, the key is generated after Bob did the measurement, and then after Bob did the measurement, Bob would not send the photon to Eva, right? There's no reason for him to do that. So that the idea that Eva, okay, can have the same information as Bob is just not true. Okay, and the final question, okay, some of you might wonder, is it possible to break this system? And well, you have two levels of answers. First is that, is it possible to stop them sharing the key? Yes, you find the fiber, you cut it, and that's it, right? And it's the same to any communication. And if you find they're using a free space channel, right, shining laser, across the air, then you just block that laser beam, and then the key distribution channel is destroyed. So in that sense, yes, you can destroy the system. Okay, and the second part of this question is, can you break into the system? And the only way that you can actually break in is to hack Alice or Bob, right? So whatever Alice send out, okay, you don't steal that information in the middle. You just directly steal it from Alice or from Bob, right? For example, the person, okay, responsible for receiving or sending this information is bought out by you. Then of course you will have the key, right? And not only the key, you can even just directly have that information. And and for that purpose, you can see that the the benefit, okay, to having a quantum key distribution is that people can save the time and energy, okay, trying to do something in the middle, but instead, okay, what they should really do is to buy out someone operating this system, and then if you guys know what that means, is that the engineer, okay, operating this quantum key distribution will be paid, very well, right? Just people trying to, avoid them being bought out by other companies or by other countries. So it would be surprised if they don't receive, $500,000 a year for such an important job and such an expensive system. Okay. And that is the part for quantum key distribution. And then you would see it in the homework, which actually I apologize because I thought I uploaded the homework last Wednesday. But then yesterday when I uploaded the homework for homework 8, I found that in the resources there's no homework 7. Okay, so so homework 7 will be due next week. Okay, and then homework 8, the final homework, will be due on Tuesday on Thanksgiving week, and then you will work on this on the homework, and then there will be one exactly the same problem, okay, on the final exam. And then the rule this year is that it's different from last year, is that only those who finish the homework will receive the solution, so that if someone doesn't do the homework, then he or she will not have the solution, and then in the final, well, they will be disadvantaged. Okay, and now let's go into the tech part. Okay, and then there's a rich history to entanglement, but then we can probably start with a little bit different approach, is by telling you what entanglement can be used for. Okay, and then the interesting thing that you might never wonder is that, probably you guys don't have the experience because most of you are too young to go to the casinos. So entanglement might revolutionize the gambling game forever. And then and I will try to give you guys an example. Okay, it's probably not the best use for quantum technology, but then it's just cool to see that. Well, I mean, in a way that all technology eventually would be used for entertainment, right? So it's not surprising that people think about how to cheat in gambling game by using quantum mechanics. Okay, now so the game that we want to play, okay, is called Devil's Gambling Game. And I will introduce how the game is played, and then there's about 15 minutes. I think I can finish that, and then we'll stop the gambling game, the classical version of the gambling game, and just proving to you guys that if you don't have quantum computing, or if you don't have quantum mechanics with you, there's no way that you can escape the devil's game. It's just like you go into a casino and then you think you can win some money. No, it's not going to happen, right? The owner always win money. And then I used to live in Los Angeles, and it's very close to Las Vegas. So actually, I visit there quite often to test whether I have my math skill with me. And then I think what I used to do, most often is that I would bring $200 with me, and then sit in the casino and then see how long I can survive. And then I think the longest I did is 2 hours, and then I just get bored and then I left. And then I don't think I ever really earned any money, but my wife did, surprisingly. Anyway, let's come back to this game. And then this game looks a little bit weird, to you guys, is because this game is set in a way that it will favor quantum mechanics, right? So if you think this game doesn't make any sense, that's normal, So that's why it's called Devil's Game, right? Because it's like normal person wouldn't play this game. So let's say this game is that, we invite 3 of you, in this classroom to this game, and then, whenever there's a teamwork, right, you have to think twice who you want to invite. And then the game, will be played 10 times straight. Right, 10 times straight. And then, you're captured by the devil, right? So if you win all 10 games, then you'll be released. And then if you lose one of them, you'll be killed, right? So you'd better have a real winning strategy, right? You can't count on probability because no matter what probability you have after 10 times, right, winning 10 straight times really require a very high probability, right? Even 90% probability of winning one hand, after 10 hands, you will lose. So the game is like this, we invite, we give nicknames here. So let's say it's Alice. 10 straight times, let's say 10x. The game is played, by someone named Alice, Bob, and then Chess, if it's not here because we want ABC. And then, so the game is that Alice, Bob, and Chess, each go into a room, right? The room is, completely shielded in a way that there's no electromagnetic field can go out, there's gravitational wave that can go out, of course, but then we're not considering that because we're talking about quantum mechanics. So in a sense that your cell phone, or the computer or the watch you bring, they will not be able to help you communicate with anyone, And then also, you cannot control what happened in the other room, right? Because in quantum mechanics, we're only discussing like electrons and photons. All of them depends on electromagnetic interaction, right? We're not talking about like nuclear, So the baseline is that, there's no communication between these 3 rooms. And then when you go into that room, you will receive a card. There's an X card and a Y card, right? So there's 2 cards. And then after going into the room, you have to choose one of the card. You have to choose one of the card. And how can we count you win? There's only 4 cases that you win. If Alice and Bob and Chess all choose the X card, you win. This is one situation you win. The other 3 situations is that if not all of you choose the X card, then if you want to win, then only one of you can choose the X card. It's like there's only 3 situations: Alice, X card, and then Bob and Chess choose Y card. And then Bob choose X card, Alice and Chess choose Y card, and then Alice and Bob choose Y card and Chess choose X card, right? That's the only 4 situations that the devil will consider you win. And then we can make it a way like this, okay? Express it in a mathematical way is that if X is 1, okay, Y is -1, then the case for win, okay, is that you want A times B times C equals 1, okay, in this case, or A times B times C equals -1 when they're all the same, of course it's 1, but when they're not the same, it has to be -1. Let me see. I think I made a mistake in defining this. Oh, yeah. Yep. So the way for you to win, okay, sorry about it. The way for you to win is that if you have A, Alice is A, times B times C, okay, equal to 1, right? For in this case, all 3 of them is 1. For this case, 1 is 1. The other 2 are -1. So when you multiply them together is 1, okay? So the chance for win, the mathematical description for winning the game is A times B times C equal to 1. Okay? Okay, now let's think about whether there's a winning strategy here. Okay? Let's think about whether there's a winning strategy here. The winning strategy here, how we define winning strategy in this case, if you play the game many times and then if you lose, you're being killed. So that the winning strategy here really means that if you use this strategy, you will win all the time. Okay? If you use this strategy, you will win all the time, and this is called winning strategy. Okay? And then let's see, there's something weird in my note. Sorry, my bad. Yeah. I haven't played this game in a year. Okay, sorry. I explained the rule a little bit weird. And then sorry about it. So the game is actually more complicated than this, okay? So let's see, okay? So sorry about it. Let me re-explain the game, okay? So when you enter the devil's room, okay, when you enter the game, you are locked into the room, you actually will receive a card from the devil. Okay, you will only be able to see your card. And your card has two possibilities. Okay, you can receive an X card or you can receive a Y card. Okay, and the way that devil set up this game is that, okay, either 3 of you all receive X card, or only 1 of you receive the X card. And the devil wouldn't tell you, okay, what situation you're in, right? And then all of this are happening at 25% chance, right? So you don't choose the card, the devil gives you the card. Okay? So imagine this, right? So if you receive an X card, there's no way for you to know, okay, which situation this is, right? Because it could be in this situation you're having an X card, and then or this situation. But then when you receive a Y card, you know that, okay, you're at the lower 3 situation, right? Because the first one doesn't even have an X card. Now, the next thing, okay, you need to do, the devil asks you to do, okay, it's a little bit weird, is that after receiving the card, you have to shout out 1 or minus 1, right? You need to shout out a number. Okay, you can see that this game is set up for binary computers. Okay, it's not set up for entertainment, right? So you shout out number 1 or minus 1. Okay, Alice, Bob, and Chaz have to independently do this decision. And then, and then here, okay, is coming the winning strategy. Okay, the case that you can win is that, okay, for the first case, when all of them receive an X card, the number they shout out, you multiply them together, has to equal to 1. Okay, for example, if all of them shout out 1, then they survive. If one of them shout out minus 1, well, if one of them shout out 1, the other two shout out minus 1, they also survive. Okay, so the number they shout out when they multiply together is 1, they survive. And then for all these 3 situations, okay, it's kind of, well, although it's 3 situations, but you know that this is symmetric, right? Depending, the only difference is the name of the person receiving the X card. The way for them to win, the way for this situation to win is that when they shout out the number, okay, and then you multiply them together, the number has to equal to minus 1 for them to win, okay? And this is understandable, right? Because if the winning strategy is, well, if the winning situation is always 1, then you guys can communicate, and then when you walk in, okay, no matter what card you receive, you always shout out 1, right? That's another game that's giving you money. So having two different situations is this is a game now, right? So when you receive the card, you don't know what it is, right? For example, if Bob and Chaz receive a card, Y card, right? Then let's see how we can play the game, okay, in a logical way. Okay, you can think that, okay, when when someone receives a Y card, he will know that we're in this 3 situation, and then the product of the shout out number needs to be minus 1. Right? Need to be minus 1. So you can discuss a little bit, okay, then when we go in there, Alice, and when we go in there, whoever received Y card, you can think, okay, whoever received Y card, let's shout out 1. Right? Shout out 1. Okay. If you see a Y card, you shout out 1. And then you let the person with X card to decide, okay, your life. And this is a little bit troubling, right? Because now if the person receiving X card always shout out minus 1, okay, in order to win this game, then if you enter the game with the first situation, all 3 of them receiving X card, and then you shout out minus 1, then you lose, right? Because in this case, A, B, C multiplied together need to be 1 for you to win, right? So the strategy, okay, the easiest strategy is that you receive Y, you shout out 1, you receive X, you shout out minus 1. In this case, okay, you have 75% chance of winning, right? If you're in this situation, and then if unfortunately the devil gives you all three X card, then you lose the game, right? So you have 25% chance of dying. Okay, and then in case you wonder, okay, if you think this is good enough, well, usually this is good enough in a gambling room. Okay, anything that's above 45% and then below 50% is considered enjoyable to play. And then if you ever think, okay, you came up with something that's larger than 50%, you're drunk, right? Because no owner of casino would ever design a game for you to win. Okay. So 75% chance is pretty good, right? You might think. And then, but if you play this game 10 times, okay, 10 times, straight times, and you want to win every one of them, then the probability is for you to win 10 straight times is only 5.6%, right? So, well, it's still, well, yeah, it's worse than getting the COVID. Okay, COVID is like 2.5% now. So, well, and then probably this is something that should scare you. Okay, this number, and okay, And what you can see, okay, how we can prove, well, so here is that you can see that intuitively, maybe there's no winning strategy, but then how do you prove it mathematically, right? There's actually, I don't know if you guys learned this from statistics, but then there's a way actually to prove there's no winning strategy. Winning strategy means that if Alice sees X car, he will shout out a number. If Alice receives Y car, he will shout out a number. He shout out that number regardless of what Bob and Chess receive or do, and then they can guarantee every time that they win. Okay, so what you can do is that you can assume that Alice, the number Alice shout out when receiving X card is AX, and then receiving Y card is AY, and then Bob receiving X card is BX. And then Bob receiving Y card shout out BY, and then also CX, CY for Chess. And then what you can do is that okay, you write down okay the cases for them to win, right? You want AX times BX times CX equal to 1, right? That's what you will win if you receive all 3 X card. And then you want AX times BY times BY equal -1, and then you want AY, BX, C, this is C, okay. CY equals -1, and AY, BY times CX equal -1, right? If there's a solution to this equation, then you found the winning strategy, right? And then what you can do is that you can multiply these 4 equations together, and then what you will get, okay, it's very simple, is AX squared, AY squared, BX squared, BY squared, and then CX squared, CY squared equal to -1, right? So you have a positive number on the left equal to a minus number, which means that these 4 equations cannot be satisfied at the same time, so you don't have a winning strategy, okay? This is how you prove that, okay, you would kind of lose, okay, eventually if you play the game long enough. And in the next class, next week, what we will do is that we'll introduce a concept of entanglement, and then we'll show you, okay, under the same situation, as long as you're allowed to bring an electron inside, okay, you don't have to communicate with each other. You have entanglement, you bring electron inside, you do some measurement to that electron, and then you are guaranteed to win this game if you do it correctly, okay? And maybe there are other, gambling game that entanglement can hack or can change, but for right now, this is the best, example I can find, okay? And that's all for today. Thank you, guys.